Hi guys, welcome back to this channel. It's very good to see everyone again. And for today's video, we are focused on 8.2 equilibrium constant. This is the part 1 of your 8.2 where we will look into a few learning objectives. We'll look into what is homogeneous and heterogeneous, and we are going to write and deduce the equilibrium constant Kc and Kp. We will also do some simple calculation for Kc and Kp. Alright? Therefore, make sure you get ready with some papers, pen and calculator so that you can join me in the calculation later on. First and foremost, what is actually homogeneous equilibrium? Homogeneous means all the reactant and product are in the same phase. In your equation, everything is in the same phase. For example, I have gases, gases, gases. That is your homogeneous. Another example, I can have aqueous, aqueous, aqueous. That is your homogeneous equilibrium. Vice versa of it, what is heterogeneous? Heterogeneous means all your product and reactant might be in a different phases. Any phases, as long as there is only one different phase, that is your heterogeneous. An example over here, I have aqueous, I have gas, I have liquid, I have gas. So I have three different phases over here, the presence of aqueous, gas, liquid, gas. So that is your heterogeneous. Another example, I have the presence of solid, aqueous, gas, aqueous. That is also your heterogeneous due to the presence of different physical phases. All the phases are very important for your Kc and Kp later on. So your balance equation must come with your physical phases. Next, let's look into what is actually equilibrium law. What is meant by law of mass action? It's actually the relationship that relates the concentration of reactant and product at equilibrium and raised to the power of its coefficient. So, the general equilibrium law looks something like this, where we are talking about concentration, alright, of the product versus the concentration of the reactant and to the power of their own coefficient. And since in the equilibrium law, we stated concentration, therefore, we are using the symbol of Kc. Don't worry about Kc, we'll look into what is actually Kc. The main thing over here that I want to show you that the relationship is product over reactant. You must take your product versus your reactant. Bear that in mind, it must be product over reactant. Next, equilibrium constant. What is actually equilibrium constant? Equilibrium constant having the symbol of K, alright? And equilibrium constant can be in two terms. The first equilibrium constant can be in concentration because of concentration. So the symbol that we use is Kc. The second equilibrium constant can be in pressure. So since it's a pressure, therefore, the symbol is in Kp. So Kc and Kp is because your equilibrium constant is with respect to concentration or is with respect to pressure. So bear that in mind, Kc and Kp are two different things. They are equilibrium constant with respect to concentration and also equilibrium constant with respect to pressure. That is how we identify Kc and Kp. Let's start with equilibrium constant Kc. What is actually meant by Kc? A very simple example I have over here. I have everything is in aqueous. Alright, so that is your homogeneous or heterogeneous. That is your homogeneous. Okay, because everything is in the same phase. And next, what would be the Kc of this equation? The Kc of this equation will be all your product concentration to the power of its coefficient versus the concentration of your reactant to the power of its coefficient. So let's see. Your Kc over here will be C concentration to the power of its coefficient times D concentration to the power of its coefficient versus the reactant. So I have concentration of A to the power of its coefficient, and then the concentration of B to the power of its coefficient. And that is how we write the Kc of a certain equation. Bear that in mind, it must be product over reactant. And since it's a concentration, therefore the bracket that you use must be a square bracket to define concentration. But we have some rules and regulation in writing Kc. So let's look into the rules and regulation. The only rules and regulation Kc having is the concentration of solid and liquid is constant. Therefore, they are not included in the Kc. So, if you are having solid or liquid in your chemical equation, that will be not written into your Kc formula because the concentration of them are constant. They won't be changing the Kc. That's why it's very important to have physical phases in your balance equation. Let's look into some example. I have an equation over here with the presence of aqueous, solid, gas, and liquid. And of course, that is your heterogeneous. Alright, due to the presence of different phases. But since the question asking for Kc, means we will only look into aqueous and gases because solid and liquid will be ignored. So we will only take count of the gas and the aqueous that present in your chemical equation. So the formula of Kc for this chemical equation will be Kc equals to your product versus your reactant. So product comes first. Product concentration T to the power of its coefficient versus the concentration of reactant Q to the power of its coefficient. And that is the formula of Kc for this chemical equation. Because solid and liquid will be not included in the Kc formula. So please make sure your balance equation must come with the physical state so that you know which one to take and which one to ignore. Next, let's look into the equilibrium constant of pressure, Kp. So we'll look into Kp now. I have a very simple chemical equation over here, the presence of gas, 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 and gas. And to write the Kp is pretty straightforward. Similar like your Kc is, we are still going to take the product over the reactant. So the product comes first before the reactant. Okay, so product over reactant to the power of its coefficient. So let's see how should I write my Kp. Kp will be equals to, since it's about pressure, or we call partial pressure, so we will write them in the form of partial pressure. Partial pressure of C to the power of C. Partial pressure of the D to the power of D. Look at the bracket, is different and we are using the symbol of partial pressure. Over the partial pressure of A to the power of its coefficient and the partial pressure of B to the power of its coefficient. And that is how we write the Kp. The main difference over here is bracket. We are no longer using the square bracket. We are now using the round bracket. And we are going to write them in the form of partial pressure. So the partial pressure will always be P and then all your product or reactant as a subscript. So you can see I write over here P for C, partial pressure of C, partial pressure of D, and so on. That is how we write the partial pressure in the Kp. So bear that in mind, Kp means pressure. Pressure, 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 pressure. But the general concept is still the same, which is your product to the power of its coefficient over the reactant to the power of its coefficient. Alright, so the general formula is still the same. We are still taking product over reactant. Similar like Kc, Kp also having some rules and regulation that we need to follow. So Kp rules is very simple. Since we are talking about pressure, therefore we only take count of gaseous state. So all your solid, or your liquid, or your aqueous will be ignored. We will only take count gaseous state in your Kp. Let's look into some example of Kp. So if you look at the equation I have on the screen right now, I have the presence of aqueous, gas, liquid. And since we are talking about equilibrium constant pressure, Kp, therefore you must only take count of gases only. We will ignore all the aqueous or liquid or even solid if there is any present. But the concept will still be very similar, where you have your Kp written, and then you will take your product over your reactant. So your product over here is partial pressure T to the power of its coefficient versus the partial pressure of R to the power of its coefficient. So we are still taking product to the power of its coefficient over the reactant to the power of its coefficient, but in the term of partial pressure. Okay, so bear that in mind. For pressure, we will only take count of gaseous state. Remember that. So as a conclusion, for Kc, we will only take count of gas and aqueous. While for the Kp, we will only take count of the gas. So as you can see over here, Kc and Kp are different. The way that we are writing is different. So make sure you read the question very carefully and check whether they're asking for Kc or they're asking for Kp. And whenever you know that you're looking for Kc or Kp, make sure you check the physical state that were involved in the Kc and also the physical state that were involved in the Kp. Don't mix them up, okay? Let's look into some simple calculation. Example 1 that I have over here is, the question stated, when the system achieves equilibrium, the concentration of CH4 is given that much, concentration of H2, concentration of CO. Calculate the Kc of the system. So we shall start by taking out all the value. So at equilibrium, alright, the concentration of CH4 given is 0.0359 molar. Concentration of H2O is not given. Concentration of H2 is 0.1545 molar. Concentration of CO is 0.0615 molar. And since the question asking for Kc, bear that in mind, Kc, we only take count of gases and aqueous. So check the physical state. I have gases, so we will take it. I have liquid, so we will ignore it. I have gases, therefore we will take it. I have gases and we will take it. So we will ignore the water over here because your water is liquid where the concentration is constant. So for this Kc, we will only take count of the 2 product and 1 reactant. And your Kc formula should look something like this. I will take count of the product. Product over here is hydrogen gas to the power of 3. And then I have CO to the power of 1. Make sure they are times over the reactant. So my reactant over here is CH4 to the power of 1 because the coefficient is 1 over here. Next, you put in the value. So the value of hydrogen gas, H2, is 0.1545 to the power of 3. Carbon monoxide, 0.0615 to the power of 1. Over the concentration of CH4, 0.0359 to the power of 1. Pick up your calculator, press it and solve it. Be careful with the power 3 over here. Make sure you press your calculator correctly. When you press your calculator, you will get 5.7420 times 10 to the power of negative 3 as your Kc answer. Kind reminder, since the question asking for Kc, make sure you only take count of gas and aqueous first. Second, since Kc is what we call equilibrium constant, alright? So Kc is equilibrium constant for concentration. Therefore, the value that you put into this concentration must be the value at equilibrium because it's equilibrium constant. Therefore, the value that given to you right now is at equilibrium. Okay? So bear that in mind, the value that you put into your Kc or Kp, they must be the value at equilibrium. Okay? Next example. Your example 2 over here, at equilibrium again is very important because you want to make sure all the value is at equilibrium before you put into your Kc or Kp. The number of mole of H2 is 0.1855, so that gives you in term of mole. And then your I2 is 1.38 mole, your Hi is 4.135 mole. In a 5 liter flask, question asking for Kc. Again, when the question asks for Kc, you know that you only take count of gas and also aqueous. So look at it, everything is in the form of gas, gas, and gas. Therefore, we will take count of everything. But at equilibrium over here, they give you in the form of number of mole, 0.1855 mole. I2 is 1.38 mole. And your Hi is 4.135 mole. The volume given is 5 liter. Question asking for Kc. Kc means that you need concentration. So we need to find the concentration at equilibrium. And the concentration at equilibrium can be calculated by using the number of mole at equilibrium and the volume. Remember, molarity or your concentration is equals to number of mole in mole over volume of solution in liter. So you have the number of mole, you have the volume. You can find the concentration. So for H2, the concentration will be 0.1855 mole over 5 liter equals to 0.0371 molar. For I2, it will be 1.38 mole over 5 liter. So for the I2, concentration at equilibrium is 0.276 molar. For the H2, similar, 4.135 mole over 5 liter. So over the volume, you get the concentration at equilibrium. So the concentration at equilibrium for Hi will be 0.827 molar. And right now, you have all the concentration at equilibrium for each and every species in your chemical equation. Therefore, we continue by calculating the Kc. So the Kc over here will be product versus reactant. So the product that I have, Hi to the power of 2, coefficient 2, over H2 to the power of 1, and the I2 to the power of 1, because the coefficient is 1 over here. So put in the value that you have calculated for the concentration of Hi, 0.827 square over 0.0371 times 0.276. Press your calculator, work it out and solve it. The value calculated is 66.7926, and that is the Kc calculated. Simple. Kc means you must have concentration at equilibrium. So what you need to do is you need to change all the information given to you in number of mole to concentration at equilibrium by using the volume of flask given to you. And that is how you work out your Kc. Another example. Example 3 over here, we will look at partial pressure. So partial pressure means the question should be asking for Kp. Look at it. So we are looking for Kp over here. The partial pressure of NO, N2, and O at equilibrium is this much. So everything is at equilibrium right now. Put in the value given. NO2, the partial pressure given at equilibrium is 2.5 atm. The N2 given 3.12 atm. Oxygen given 1.89 atm. And all that is the pressure given at equilibrium. So we can use it already because it's the value at equilibrium. And write the formula of Kp over here. My Kp equals to product versus reactant in the term of partial pressure. So partial pressure of N2, that is how we write it, to the power of 1, because the ratio is 1, times the partial pressure of O2 to the power of 2, over the reactant that I have, partial pressure of NO2 to the power of 2. Substitute all the value. So the partial pressure of N2 over here is 3.12 atm times oxygen 1.89 to the power of 2 over partial pressure of NO2 2.5 to the power of 2. And when you press your calculator, the answer that you calculated is 1.7832, and that is your Kp calculated. Kind reminder again, is always product versus reactant. So make sure you're taking your product to the power of its coefficient over the reactant to the power of its coefficient. And since we are looking for Kp, make sure the bracket is round bracket. And a bit of reminder over here, the unit of the partial pressure can be anything as long as they are the same in one question. So if everything is given in atm, everything must be in atm. If everything is given in Pascal, then everything must be in Pascal. If everything given in torr, then the rest must be in torr. So the unit of the pressure can be anything as long as they are the same in one question. Last example for this video. At 580 Kelvin, the equilibrium Kp is given. For the reaction below is 9.45. So slightly different question. The question gives you the Kp. When the system achieves equilibrium, we already achieved equilibrium. The partial pressure of N2 is this much in torr. H2 is this much in torr. Calculate the partial pressure of ammonia. So we are looking for the partial pressure of ammonia with the Kp given. Take out all the value. So pressure at equilibrium for nitrogen is 0.435 torr. For hydrogen is 1.15 torr. So the question asking for the pressure of ammonia at equilibrium, that will definitely also be in torr, because like I said previously, the unit must be the same. The Kp over here is given. The Kp of this equation given is 9.45. So slightly different. The question gives you the Kp. We are looking for the partial pressure at equilibrium. But the way that we solve it is the same. So we start off with the formula of Kp. The formula of Kp, again, your product versus your reactant. I started off with my product. Product is ammonia over here to the power of 2. My reactant is the partial pressure of N2 to the power of 1, and the partial pressure of hydrogen to the power of 3. So that is my Kp formula. The Kp given is 9.45 given in the question, equals to, we are looking for the partial pressure of ammonia. We are looking for it over the partial pressure of N2, which is 0.435 torr to the power of 1. Partial pressure of hydrogen, 1.15 to the power of 3. And that is everything after you substitute. So you can see that you can solve your mathematics and Last but not least, you will be able to get the partial pressure of ammonia after you square root it. We only want the partial pressure of ammonia, so make sure you square root it. The partial pressure of ammonia calculated will then be 2.3316 torr. Make sure the unit torr is there because it's a partial pressure of ammonia. In the question above, every pressure is in torr, so the ammonia will also be in torr. Bear that in mind, we're only looking for the partial pressure of ammonia. Make sure you square root the value after you calculate. We don't want the power of 2. We just want the partial pressure of ammonia. So make sure you square root them before you write the final answer. So that is the final answer of the partial pressure of ammonia in torr. Very simple. A bit of conclusion over here. First and foremost, make sure you check your chemical equation and they must be balanced before you use it because we are going to use the coefficient. So to make sure that your coefficient is correct, you must make sure the chemical equation is correct. Next, you must ensure your chemical equation having the phases of each species because we are going to identify whether we need to use it or not in the Kc or Kp. Bear that in mind, for the Kc, we only take count the gas and also the aqueous. For the Kp, we only take count the gas. So it's very, very important to know the phases of every species in your chemical equation. Last but not least, read the question carefully. Check whether they are asking for Kc or Kp. Because Kc, you will take different thing. Kp, you will take different thing. And the way that you write it also different. Because Kc will be in a square bracket of concentration, Kp will be in a round bracket of partial pressure. But generally, the concept is the same, where the concept is still your product over the reactant. So there will always be product over reactant. Don't forget their coefficient from the balance equation. So it's always product to the power of its coefficient over the reactant to the power of its coefficient. And that is everything about Kc and Kp and also some basic calculation about Kc and Kp. We'll look into more calculation in your part 2 later on. So don't forget to like this video and also subscribe to my channel for more videos. I'll see you in the next video and thank you for watching.